Good morning students. Today we will start the chapter derivative. In this chapter we will learn how to measure rate of something. We can see an example. Like suppose I put a ice cube, solid ice cube on my palm. Okay? And obviously due to the heat of my hand it will be melted. Let's say after 2 minutes it will be completely melted. So that means during those 2 minutes, here the whole surface temperature is changing. So if that is changing and we can measure that change of the temperature every second, then we can see that there is a pattern of change. We can see that pattern if we can measure that change. So for this type of calculation, basically, if we can do that, it will help in it is a very small example, but it can help in very big things, big practical things. So this type of calculation actually we can derive with the help of derivative. Or in other words, we can say derivative is an instantaneous rate of measurement. Means at very small time something changes, how much something changes, that we can measure through derivative. That is the beauty of derivative. So basically in physics you will see a lot of use of derivative, but in math you have to know the theory. And here in mathematics we do almost every operations on functions. So here like in limit you have done limit on a function at some point. Here in derivative we will also do derivatives on functions. Basically in mathematics, in our syllabus, what we will see that for how much changes in x, how much changes happen in fx, that we will see, and through that we will know different properties of derivative. Okay. So let's start the chapter. Derivative. Okay. So here we can see that we know that our function is denoted by y equal to fx, right? So this is our y-axis, this is our x-axis. Okay. So x-axis represent the variable x, independent variable, and y-axis represent the function, means the y. Okay. So let's say this is a graph of a function. Okay. I suppose that this is a point x. This is a point x, okay. And I am going in the right hand side h distance more. So it will be x plus h distance more. So this is what? This value is fx. This value is what? F of x plus h. So for changes, here changes happen, h change occurs. So due to change h in the input, how much change happen in the output? That is f of x plus h minus fx. And changes in input happen x plus h minus x, or we can say that f of x plus h minus fx by h. Now for instantaneous rate of measurement, which is actually called derivative, this h should be very much smaller. And h should be such smaller that, in verbally we can say that h is such smaller that we cannot see h by eyes. Only eyes, we cannot see it. Means that much smaller. So how that much smaller changes we can define? It cannot be defined by any number. It can only be defined if we define h as h tends to 0. Because h tends to 0 means what? H tends to 0 means h is almost 0, but h cannot be 0. Obviously h is a value, but h is almost 0 also. So that means h is a very, very small. How much smaller you think? Maybe much smaller, then this also possible. Means if you think that h is 0.00000000 something around, even smaller than this number is also possible. If I can put 0 here again, it will be much smaller than this one. So h can be very much smaller if we say that h tends to 0. So if this thing we apply in this expression, then we will get instantaneous time, and which is actually called derivative. So derivative is our limit h tends to 0 f of x plus h minus fx by h. Okay. So this is called derivative. This is called derivative. It is represented by, how we represent derivative? It is represented by d by dx, or we can represent as f dash x. Okay. In this way we represent derivative. Now this is the derivative definition, and obviously derivative only exists if this limit exists. Okay. So one thing here, f is a real valued function. F is a real valued function, and the above limit exists, then we can call that f dash exists. The above limit exists. Then we can say that f dash x exists. Okay. And in this way, when we do the derivative, that is called first principle of derivative. It is called first principle of derivative. It is called first principle of derivative. In this way, we can do derivative at any point of x, or we can do the general derivative of a function. We can see an example. Solve a question by first principle of derivative. Evaluate f dash x when fx equal to sin x into cos x. Okay. We have to do this function derivative by first principle of derivative. What is our first principle? We have already discussed. Okay, let's start. So by first principle of derivative, f dash x equal to limit h tends to 0, f of x plus h minus f of x by h, right? So we can write that f of x plus h means just replace this x by x plus h, sin of x plus h into cos of x plus h minus sin x cos x. In denominator it is h. Now we have to apply some trigonometric identities so that we can simplify it. You can see here that this is like sin theta cos. I think because of heat, video is cut. So see here again what we have done here. We have used here identities. We have multiplied 2 in both the terms, and we have multiplied here 1 by 2. So expression doesn't change. So it is 2 sin theta cos theta means sin 2 theta. So it will be sin 2x plus 2x. It will be sin 2x. Okay. Now we can use here sin c minus sin d formula. What is sin c minus sin d? It will be 2 into cos c plus d by 2 into sin c minus d by 2. Here c is what? 2x plus 2h, and d is what? 2x. Okay. So we have here 4x plus 2h by 2, and here 2h by 2. Okay, so here after simplifying, after cancelling 2 in both numerator and denominator, we get that cos 2x plus h. Here we get that 2 to cancel, we get sin h. Okay, by h. Now here in this term I can put 0 here, but I cannot put 0 here because then it will be 0 by 0 form. So put 0 here, it will be cos 2x. Okay. Now sin h by h, limit h tends to 0, sin h by h. What is the value of it? We already know this limit. So this limit value is 1. That we have put here 1 into 2x, cos 2x. So our answer is cos 2x. Means this function derivative is cos 2x. And by first principle of derivative, we can derive derivative of any function by this process.